thanks to Mal for suggesting this topic in the first place. Even really more profuse thanks to Mal for reminding me on Sunday morning when we encountered each other on a beach walk that I was on today. so bear that in mind. What it means is that the toys are not as prolific as they would otherwise have been, but anyway, we'll make do with what we have. So let's look at geomagnetic reversal. What the hell does that mean? And I guess the subtitle, how trustworthy is your compass? And if anyone's tried to ever use a compass in a serious way, you know it's not super trustworthy anyway, for lots of reasons, because you might have a bit of iron in your pocket or something. But anyway, let's see. So what is geomagnetism? Big word, with or without the hyphen. And it's the magnetic field of the Earth. The Earth apparently has a magnetic field. A lot of planets have magnetic fields, but not all. And we'll see more about that later. So there's a picture of a magnetic field. This is, we'll come back to that picture quite a bit more later, but it's meant to depict the magnetic field in a pictorial way, and we'll see as we go on how you can represent magnetic fields with pictures. First of all, before we go any further, pictures are going to dominate the discussion. There won't be any equation. Well, there's one equation. It's got two terms in it, so only one equation, but lots of pictures. So, what's a magnetic field? Well, that was the segue into this question. Magnetic field. Well, it describes the magnetic force between objects. That didn't really help much, has it? So, how does it work? One of the objects produces this thing, the magnetic field, and the other object experiences the force produced by the magnetic field. So, it's a mutual interaction between two objects, and the field is it's a human construct. It probably isn't physically real. You can't put your finger on a magnetic field. All you can do is observe the effects of our hypothesized field on by producing the force on another object. And of course that works both ways around. One object produces a field, exerts a force on the other, and vice versa.
Can you just move slightly? I think people on the side can't see
Oh,
the
I
screen.
see. Right, gotcha. Or I can stand more this way. Yeah.
Much better geographically.
Okay. So what does all that mean? Well, we'll come back to some details on that. But before, the best way is to see we can get some intuitive understanding for how this works. So this is where I had planned a large number of demonstrations. I only managed to have a small subset, but don't worry, I've got nice pictures to substitute for my otherwise toys. Right, okay, so we'll start with historical thing. It was discovered that if you had some materials and you suspended them so that they're free to move, they will always line up in a certain direction. And this is a magnet. I took it off my fridge this morning. I know it's a magnet. And in fact, there's 6 magnets just joined together because one you wouldn't see, just one. All I've done is I've got a bit of cotton out of the sewing cabinet and suspended this. Actually, I'm going to suspend it a bit higher because there's steel screws holding this together. So I will take it up a notch or up a knot, whichever way you prefer. And so this is how magnetism was really first discovered. Simultaneous discovery of magnetism and the fact that the Earth has a magnetic field. Because and this is what I was saying before, it's a mutual interaction between two objects. One object is the Earth, which has a magnetic field, and the second object is this magnet which experiences a force from the magnetic field, and the force, because it's tended by a bit of string, the force can't do anything other than rotate it. And so what it does, it rotates and aligns itself in a particular direction, which we will see as the talk unfolds. The direction in which that magnet is pointing is exactly parallel to the local spot value of the Earth's magnetic field. So it's pointing down into the ground a little bit, but it's also pointing north. So that's what happens. That's a demonstration of the interaction between the two objects through their magnetic field. Okay, so I would have liked to have had a permanent magnet. I've ordered some super magnets online. They're still on their way from China, so I'm sorry I can't do the permanent magnet demonstration, but you know, there's a historical picture of a permanent magnet picking up a piece of iron, and that's you know, pretty familiar to most people. Magnets exist and they can pick up things, so that's important demonstration nevertheless. Again, we see there a mutual interaction between the horseshoe-shaped object is one object, and the iron is the second object, and that interaction is mediated by what we call the magnetic field. So we can use an electromagnet. Again, I didn't have time to make an electromagnet. This is a magnet that was made by Mr. Henry. He's got a lot of electrical and magnetic units named after him. He built this in the mid-1800s, and it was able to lift 300 pounds. So he was pretty pleased with that. And there are more modern variants. This photograph was taken in 1911, where they're using electromagnets to pick up lumps of iron off the scrap heap. And how does it actually work? It works like that. You have, yeah, we're going to get this laser pointer to work.
Yeah,
It's
the laser
switch.
No, the laser point out.
No, anyway, it doesn't matter. There's a horseshoe-shaped piece of iron, and it's got a wire wrapped around it, and you pass a current through the wire, and it produces this magnetic field, which exerts a force on that second object at the bottom. So that's how it works. So it's pretty clear then. What we're looking at here is, in the electromagnet, we've got circulating electric current. And if you think about what's going on inside the permanent magnet, it's got circulating electrons. Electrons are charged. We'll come to that. Don't worry about it. So it looks like, you know, the key to magnetism is to do with currents going around in circles. Well, but you can make magnetic fields from straight wires as well. And again, I'm sorry that this is another dud. Yeah, you can have some light. Another dud demonstration. I have two wires which are straightish and just sagging a bit by the way they're meant to be straight. And they're hanging there in the Earth's gravity field. And the object of the exercise is to pass a current through, but my car battery doesn't have enough, and it's so puny, the effect, that you hardly notice it, so it's a bit of a disappointment. The bottom line is, let's use our imagination. Let's say I had a really good battery, maybe a 100-volt battery, and passed the current through these wires, and then if I pass the current through both wires, if I pass the current through one wire by itself, nothing happens. If I pass the current through both wires in the same direction, doesn't matter whether it's that way or that way, I can just connect my battery to each end and pass the current either that way or that way. In both cases, what happens is a force of attraction between the two wires and they stick together. So imagine this is happening by a battery, not by my fingers. And if I jig the thing slightly differently and have the current passing in opposite directions, so going this way in one wire and that way in the other wire, then there's a repulsive force, and the wires fly apart. Now this is a demonstration that I do for my students every year. I'm just sorry I didn't have time make it work properly. You need about 50 amps in a piece of wire to get a force that's worth looking at, and I'm only managing to get that 1 amp. It goes as a square, so we're way behind the 8 ball for making this work. But at least something to look at. So you don't need circulation of current to make magnetic fields. So I think this slide is something I showed in my previous talk, and I think for those for whom it's repetitive, I apologise for the repetition, but I think it's really important for a number of ways. It puts our magnetism into context, and it also tells you that we're pretty well okay with understanding the fundamentals of the interactions in the universe, and I think that's a really important thing. So this magnetism is something that's quite well understood in the context of all the others. So there's 4 interactions between the entire universe, between every lump of matter in the universe can interact with any other lump of matter in the universe in only one of 4 ways. Now there's a little bit of speculation, there might be a 5th one that hasn't been conclusively identified yet, so I'm not adding a 5th line to my table. You'll also notice there's no clairvoyance or extrasensory perception. These interactions are something that are quantified, they can be measured repetitively. Anytime you want to measure a gravity force, anytime you want to measure an electromagnetic force, you can do so anywhere on the planet, presumably anywhere in the universe, certainly as far out as on the moon, all the experiments that have been done, and the solar system itself seems to be governed by these interactions, so they're totally understood. So let's have a quick look. So the thing that gives gravity its action is the mass. If an object has got mass, it will have gravity. And it's got an inverse square law. I guess that's the other thing. I wish I had a laser point. Now this one, I'm not going to say much about that. This holds the nucleus of an atom. One of the forces that holds nuclei together. And I won't say too much about that. Electromagnetic, that's the one we're going to be really interested in. Electromagnetic is the name of the interaction of which magnetism is a component, a very important component. And the thing that makes the electromagnetic interaction, the property that you need is charge. Now some fundamental particles have charge, others don't. We'll say more about that later, but it's a charge that's the important property. So an object can have a mass and a charge. It may or may not have a charge, but it will certainly have a mass.
Frank, can you explain what you mean by 10 to the minus 38 or 10 to the minus?
Oh, that's the relative strength.
Yes.
And it's a sort of a normalised strength. If you take two typical objects and say, for example, if I take 2 electrons and calculate their electromagnetic force, it'll be 10 to the 36 times stronger than their gravity force. That's and for the nuclear ones, it's a little bit more nebulous than that. I don't want to go into, but it's certainly you can ask the question about electrons or protons or any other fundamental particle. You know, the relative strength is just given by the force on typical relative force. The other important thing about the electromagnetic, it's a long-range interaction with an inverse square law. And then there's another nuclear interaction. Again, I don't want to say anything much about that. Gravity, what do we know about? What's important about what holds us to the Earth, holds the Sun together, holds the solar system together, holds the universe together. It's the pervasive force that's out there and it's really important when, oh great, that's fantastic, when the mass and all the distance is large. That's the dominant force. I'm just going to go through that. It works on a tiny scale. there's no everyday familiarity. You have to do nuclear physics to experience the weak force, so we won't go there. Electromagnetic. Now that is a really important interaction. It holds everything together. Ordinary things that you're familiar with. It makes solids, liquids and gases. It makes all of chemistry is to do with the electromagnetic interaction. Everything that you know about chemistry can be explained by the electromagnetic. Everything you know about biology can be explained by chemistry, therefore by the electron. Everything in engineering, everything in electronics is part of engineering. All of these things depend and work purely by the electromagnetic interaction. Music, sound, springs, strings, instrument, everything is electromagnetic, and so on. Works on everything. So it's pretty important, and it's worthwhile getting a bit of an understanding. And strong force, again, it's another one that doesn't have any everyday familiarity. So I already said that the property that gives rise to the electromagnetic interaction is electric charge. Charge is just a property that some elementary particles have, and so every object in the universe may or may not have a charge. But charge is quantized. Charge comes in specifically sized lumps. We'll say more about that later. And unlike mass, which is always positive, charge can have either sign. And that's a really important part of electromagnetism. And yet, atoms, even though they contain particles, fundamental particles that have charge, atoms are basically neutral. You can make atoms that are not neutral, but it's hard work. Atoms are basically neutral. There's an example of an atom. It has a nucleus with some positively charged particles in it, and it has some electrons floating around which are negatively charged, and because the charge is quantized, the magnitude of each charge is the same, and there are equal number of electrons and protons, and so the total charge of the atom is zero. Exactly zero. Not approximately zero, not zero-ish, exactly zero, as far as has ever been measured, because of this quantization of charge. Every charge is the same size as every other charge. The only thing that's different is the sign. So electromagnetism is basically, therefore, a study of or a manifestation of the forces between charges. And we're interested, because it's a geomagnetism discussion, we're interested in the magnetic force. And they're produced by and on moving charges. We've seen currents, producing magnetic field, magnetic forces. So it's moving charges. Of course, if the charges are stationary, they still have interaction, but that's called the electrostatic interaction. And all you need is a positive and a negative charge. So let's look again. Charge is quantized. Every charge you can subdivide into multiples of this. Now there are more digits known. I think it's that fundamental quantum of charge is known to maybe 11 digits or something. It's quite amazing. But every charge, you can count the number of charges in any piece of stuff.
Frank, can you just explain what 1.6 times 10 to the 19 means? A lot of people probably aren't familiar with exponential notation.
Okay, so it's 19 digits. 19 is 0.19 Right, so it's a crazy way to write it because you need a big piece of paper to write it that way. So
what is C? What is C?
And C is the fundamental unit of charge named after Monsieur Coulomb. It's a unit of charge, arbitrarily designated name, Coulomb, abbreviation C. Well, thanks for asking that question. I should have defined that. So in ordinary experiments when Coulomb was first defined, there are lots and lots of charges. Many electrons, many protons make up a lump of material that you play with, and so that's why the charge on its individual atomic particle is so tiny, because there's usually lots of them together.
How do you spell Coulomb, please?
Sorry?
How do you spell Coulomb, please?
C-O-U-L-O-M-B, I think. Mr. Google will tell you for sure.
Thank you.
So there are two kinds of charges, positive and negative, and probably, now there are equations for this, which tells you the size of the force in relationship to the charges and the distance between them, but we don't need an equation. The important thing is that unlike charges attract, like charges repel, and what you see there, the lines with arrows on them are called an electric field as opposed to a magnetic field. Once again, this is a construct that we use to help us understand the electrostatic interaction. The interaction between stationary charges is mediated by this thing that we call the electric field, and it makes beautiful pictures. And you can almost see the attraction, because those lines are drawing the two objects together when they're the opposite sign. Because an electric field line always starts with a positive charge and ends up on a negative one. So it's like it's drawing them together. When you have two like charges, in this case the example is two plus charges, all the field lines emanate from the plus charges, and that's pushing them apart. So it's quite graphic. And in your physics text, elementary physics textbooks, they introduce the idea of electrostatic attraction by taking some objects, and a typical object is a little piece of cat fur. I mean, I presume it's a deceased cat that's given up its fur in benign ways, and if you rub that fur on a bit of something else, like a cloth or something, it will then pick up little scraps of paper or other light insulating objects. And if you can do it with your comb, you take a plastic comb, rub your hair vigorously, you'll be able to. Or you can do it with your rubber shoes. If you walk on a carpet in a very dry environment, walk on and then touch the door handle, you feel the effect of the electrostatic charge. So there are many ways you can experience it. You don't get it so much in Tasmania, but in Perth it's a real problem. If I slide out of my velour seat and then touch the metal part of the car, I get a zap, because I'm rubbing charge. My jeans are rubbing charge off the velour cloth. Anyway, so here's someone. Here's a cat that didn't. Here's a cat whose fur was rubbed in vivo, and it trapped all these little bits. It's real. So rub a cat fur and you'll attract little scraps of stuff. Okay. And I'm sure it's familiar to most people, but not in this form. But taken with this flow. So that was the electrostatic interaction, pretty much taken care of. Just stroke a cat and you've got it. By the way, there's not much charge involved in doing that. You don't transfer a lot, not many coulombs. Because it's really hard, we'll see later, it's really hard to separate the charges. So what I'm going to try and convince you now is that magnetism is an effect of relativity. I had to work relativity into this equation somehow. So what does that mean? Well, it's a relativistic correction. You know, relativity is something that was invented by Einstein to explain some tiny little nuances that are observed in various parts of the universe, not really realizing that it was fundamental to the action of the magnetic field. It's a relativistic correction to the electrostatic interaction. So all things in relativity, here's my one and only equation. All things in relativity are governed by the factor V over C, and it's all squared. V is the velocity of the charge, and C is the speed of light. Speed of light is pretty fast, 300,000 kilometres in 1 second. So it's fast, but not fast enough, because it's what's limiting at the moment the speed of computers. We need to make them smaller so that the signals can get from one part of the computer to the other in a shorter time. That's an aside, anyway. So, okay, well now we need to know what's the speed at which charges typically move when you've got a current, say. Okay, well, this is where we need the light demonstration. I would like you to really concentrate, not yet, when I say concentrate, watch the switch, and I know this is impossible, you've got to watch the light and watch the switch simultaneously. Turn it on. So how far was the delay before the first, pity they're fluoro, pity they're not, turn them off again? What was the delay? Pretty imperceptible, tiny delay. Right? So that it's turning it off, it's probably about. So, right, so it's a tiny delay. So you'd think, speed of charges, because you've got this charge got to get from the switch to the light, the speed of moving charges must be huge. You can't even see the delay. Maybe it's, coming on for being the speed of light. Well, this is where you would need an equation, but I actually didn't need an equation. I googled drift velocity of electric charge, and there's an online calculator that says type in your current, type in your material. I typed in copper wire, most of the wires in there. I typed in the diameter of a copper wire, the millimetre, typed that in. I typed in 1 amp, and it gave me a speed. And I had to look at it really carefully. It gave me a speed which is a 10,000th of a metre per second. That takes 3 hours for the charges to move a metre if you've got 1 amp flowing in a wire. How can that be? So how is that consistent with the fact that when you switch the switch on, the light comes on almost instantaneously? There's no delay. I mean, how many metres from the switch to the light? We're talking about a day, roughly, for the charge you get from the switch to the light. What's going on? What are we missing? Time for a demonstration. Well, the demonstration is already about the light switch has already happened. So now I have another demonstration which I routinely give to my students when I'm teaching them electromagnetism. And what I have is a piece of clear plastic. I didn't have time to go to Bunnings. This would have been an easy demonstration to do. So you imagine a piece of clamped here and here, a bit of U-shaped plastic pipe, bung in a funnel at one end, and fill it with water. And you can see I'll use this beautiful stick. You can see the water level. It's there and there, at the same height, because the tube is full of water. And then I'm going to add some more water. That's why I've got the funnel there, so I don't miss. I'm just going to get a watering can, and it's got coloured water in it, so I can tell what water I've added. And of course, as soon as the first drop of water hits that funnel, it raises the level and pushes water out the other side, and there's no delay. Well, is there a delay? We can debate that in a moment. Nothing's really instantaneous. And so but of course when you see that coloured water moving, as it moves actually quite slowly. It takes, for a typical watering can and a bit of 1 centimetre plastic pipe, it takes nearly a minute to get to the other end. And yet the water starts dribbling out straight away. As soon as you start pouring into the funnel, the water starts dribbling out at the other end. So it doesn't matter that the water is actually moving very slowly. It emerges, dribbles out instantaneously, just like the light switch did. And for the same reason, in fact, exactly the same. What is that reason? What is the reason that the water dribbles out at the end almost instantaneously and the light comes on almost instantaneously? And the answer, clearly, is because it's full of water. It doesn't need to wait for my coloured water to get to the end before water starts dribbling out. It doesn't need for the new water to come to the end. The old water that's in there already gets pushed out almost instantaneously. And for, I know there's going to be people that are curious, why do I say almost instantaneously? What is the delay? What's the mechanism? What could be the mechanism that causes the delay? It's not exactly 100% instantaneous. What slows it down? And any suggestions? What could it be that slows it down? Yeah.
Surface tension.
Surface tension is one, yeah.
Inertia.
But it's not the main one.
Inertia.
Inertia, did someone say inertia? I love it, yes, inertia. You've got to move that mass of water. But there's something else as well, because, you know, this the immovable force and the irresistible force and the immovable object. If I push hard enough, it'll come out. So the other thing is the springiness, the compressibility of the water. Because if I add water to this end, it squeezes the water, and that is a pressure wave that gets to the other end. And so it's the speed of sound in water that determines the delay. So if that's an aside, it's not important, but it's kind of amusing if you're interested in that kind of thing. So the thing that causes the delay is that the information about that we've added pressure to the right-hand side, that information has to travel through the water to get to the other end and before the water can start dribbling out, and it's the pressure wave that goes down there, and that travels at the speed of sound. And the speed of sound in water is about 3 times what it is in air. So air it's 300 metres a second, in water it's about a kilometre in a second. So it's a pretty small delay. If that's a metre, it's a thousandth of a second delay between when you start pouring and when it starts dribbling out. But I haven't factored any surface tension effects in there, so that may change the equation a little bit. Okay, well, having said that, kind of tells us an interesting further question. Is it interesting to speculate what it is? Is there a delay between when you turn on the light switch and when the light comes on? Is there a delay there? You know, because the reason that light comes on straight away is that the wire is full of charges. You know, it's made of ordinary matter with protons and electrons in it. It's full of charge, and when the current flows, it's actually the electrons that do the moving, and they only move in metals which conduct electricity. So when you turn the switch on, what happens is, just like the water, new electrons are added in at one end to the wire, and immediately they start emerging from the other end and illuminating the light. Except there is a delay, just like in the water, the delay was the speed of sound.
Is inertia then parallel or the same as resistance?
So
Is inertia with respect to that the same as resistance?
No, inertia is the same as inductance. Resistance is the same as viscosity, but that's a whole new topic. The resistance is the equivalent of the viscosity of the water, which is the water drag. That's another thing that slows it down a bit, but it's not relevant in this instance.
Right.
And so the resistance doesn't matter either. It doesn't matter what the resistance. It's still instantaneous, unless I'm not going down that road because we could be here all day. So, what determines how fast the information that the electrons have gone in at that end of the wire to get to the light? And the answer is it's the fastest speed there is. It's the speed of light. That's the wave of information has to travel down that wire to get to the other end, and it can do so only at the speed of light. Now, the speed of light, as you know, is pretty fast, so it really is an imperceptible delay. Moving right along. So it can't be, and we're talking about a relativistic correction which scales as V over C all squared. V is 10 to the minus 4, and C is 10 to the plus 8, give or take a factor of 3. And you've got to then divide that and square it. That's kind of tiny. How can that possibly be right? It just doesn't seem possible that magnetism is a relativistic effect. Because we very rarely experience electrostatic forces, and even if we do, they're just weak. Like maybe you can get a bit of foam to stick to a cat, that's pretty puny force. And yet, magnetic forces, they can pick up hundreds of kilograms of scrap iron, they can make electric motors work, all of that stuff, make electric bikes work, all of that stuff, big forces. How can it be? And the answer is, it's like a 0 divided by 0 question. If that means anything, good. If not, don't worry about it. The universe is just incredibly neutral. Atoms have the same number of electrons and protons, so they've got no net charge. And so the number of plus and minus charges in the universe is exactly balanced. And it's really hard to make them unbalanced. And so therefore it's very hard to contrive in real life a situation where the charges are separated to give you a decent amount of electrostatic force. It's almost perfect. Electrostatic forces between you and me and between objects are almost zero. In fact, they are zero to as many digits as you want to measure, because we're all so neutral. And so the electrostatic force is zero. And so it doesn't matter that when the charges move, it's a tiny fraction of the electrostatic force. But it's the only thing. So when the charges move in a neutral system, their magnetic force is tiny, but it still dominates way over the top of the electrostatic force, because everything's so neutral. And that's what happens if things are not neutral. It's really, as you can see, I don't need to describe any more the obvious, that when you try and separate charges, like put a few excess charges from the ground up into a cloud, that's what happens. It's very hard to create a charge imbalance. So that's why you don't normally feel the electrostatic force, and that's why you do normally feel the magnetic force. So, all right, that's now we've got to do a little bit of hard work. We've got to try and figure out what these magnetic fields are that are produced by moving charges. And I'll start off, this is just a pictorial, there are equations for this, but this is a pictorial. Those circles represent the strength of the magnetic field that emanates from a moving charge. And so the further away from the axis, the stronger the field. They're contours of equal field. So that means that closer to the charge, the field is much stronger. That's a single moving charge. Now, as we've seen, it's very hard to get single moving charges without getting lightning and other things. So single moving charges or single charges are hard to get in real life, whereas it's easy to get a current flowing in a wire. And so what's going on there is that the wire is still neutral because it's got protons in the nuclei of the atoms, and it's got electrons which flow. They're the things that are doing the flow. So we're able to separate, not physically, but separate by their relative motion. We have electrons moving and the nuclei in the material staying in place. And so those moving charges create a magnetic field. And again, you will see the contours of magnetic field, and it's getting weaker as you get further away from the wire. It's the same strength. Whoever drew this didn't bother to continue with the picture, because these should be drawn at regular intervals all the way along. And if anybody wants to know, you can predict the direction in which the magnetic field lines circulate around that wire by the right-hand rule. I don't think I have time to describe the right-hand rule, so we'll just let one. Here's a pictorial example where you can actually This is a transparent sheet with a hole in it and a vertical wire carrying a current, and just sprinkle some iron dust, and the iron dust particles just line themselves with the magnetic field. You could do the same experiment if you had that compass and just moved it at different places around. The compass will always be pointing tangentially.
Can you just explain what this right-hand rule is, please?
No, not right now. I'd love to, but I'm not going to let myself get diverted. So here's the magnetic field. Again, pictorial, there are equations to describe this. I guess the important take-home from this is that there's a symmetry axis with a straight field line there, and they circulate around here. It looks just like this is a tiny segment of a straight wire. We won't ask how the current gets into that loop, presuming it's broken somewhere, there's some wires coming out, but it's a nice picture anyway. And you can have lots of loops in a spiral. It's called a solenoid. Here it's realistic, it's got leads coming in to allow the current in and out again, and it's got field lines again. There's the axis of symmetry. So what about a permanent magnet? Example of a bar magnet. This is the field lines. They look familiar. They look pretty much the same as the field lines in the solenoid. What that tells you is that we know that in the solenoid it's a circulating helical current. So presumably in the bar magnet there are circulating currents equivalent in the bar magnet that look very similar. Not the same, but very similar. Here's an example of practical use of the solenoid. If you've ever been for an MRI, there's a whack-a-grade solenoid, which is this guy here, and it passes a fairly big current, produces a magnetic field. And the reason that it's enclosed in that casing is that the solenoid is kept at very low temperature so that you can have a big current without getting a lot of heat. Okay, so I'm going to skip that slide, and this won't be long now before we have our pause. So this is a movie, but I don't think we need to. We've seen all the ingredients of this movie. Basically, we have a bar magnet. We've got it just underneath the transparent sheet, and we've got a compass. We can move that compass and sprinkle iron filings on top, and you can see them lining up with the field lines. And if we move the compass underneath there, the needle always points in the direction of the field line. That's the important thing about the magnetic interaction. So, finally, the Earth's magnetic field. Took a while to get there, but I think we've got enough background now to see how this works. Let's get rid of that ugly title. So there's a pictorial view of the Earth's magnetic field, and you've got sort of like three axes in this picture that try and explain what the axes are. Let's start with a B-axis. So this is the B-axis that intersects the Earth's surface at B1 and B2, and that axis represents, if you try to approximate the magnetic field of the Earth by a bar magnet, that's what its direction would be, and this is the axis that it would have, and it's about 10 degrees away from the axis A. Axis A, that's drawn there. That's the spin axis of the Earth. So that's the real, A1 is the real geographic north pole, and A2 is the real geographic south pole. But now you'd be tempted to think that B1 is the magnetic north pole, but it's not, because the approximation that it's a simple bar magnet is not very good. There's not actually any symmetry line. You can see that the field lines are drawn. There's no simple symmetry line. But if you say, well, the North Pole is where the magnetic field is locally the strongest, then you'd have to pinpoint it there. And if you say the South Pole is where it's strongest in the opposite direction, you'd have to pinpoint it there. So that's the They don't fall in a straight line. So the reality of the Earth's magnetic field is very complicated. It's not just a simple bar magnet. Only about 85% of it looks like a simple bar magnet. The other 15% is like lots and lots of bar magnets sprinkled inside the Earth to produce the actual observed magnetic field. Here's another view of that. Now, the important thing about this one is that the magnetic South Pole is close to the geographic North Pole. How can that be? Well, of course it has to be, because when we first started playing with bits of stuff, we defined in this magnet the North Pole as a bit that points north. But because of the magnetic interaction, unlike things attract and like things repel, if our compass is going to point to the north, that must be the south magnetic pole. And of course you can also see that it's only at the equator is our magnetic field horizontal. So if we move this apparatus to the equator, that magnet would be horizontal. As we move away from the equator towards the poles, it starts to dip into the Earth's surface. And this is just the approximation that the Earth's a perfect bar magnet, but it doesn't matter, it illustrates the point that I wanted to illustrate. So if you want the reality, this was measured in 2011, I think. It's hard. Satellites are making these observations all the time. This is the strength of the magnetic field at the surface of the Earth, as measured. And it's in units of nano Tesla. Tesla is a unit of magnetic field. Its magnetic field is measured in Tesla. So typically fields are a few tens of millions, a few tens of a millionth. So this would be like 40 millionths of a Tesla, 440,000 nanoteslas. So there's quite a variation across the Earth's surface, nearly a factor of 2 in the strength of the field. We're in a pretty strong field here. So if you're in a magnetic healing, you're in a good place here because you've got nearly twice as much field as those poor buggers up there. So
does that distort your navigation with compasses?
Well, this is only the strength. So as long as your compass doesn't have too much friction, it will still be the dominant effect on your compass.
What they call ley lines?
What's that?
Are they ley lines?
L-E-Y.
Ley lines.
No, they're not. They're a new age phenomenon, Frank. You may not know.
This is a contour diagram. Pretend we've got contours, the hills and valleys are the size of the strength of the magnetic field. That's all I can say. Okay, there's the direction as well. I mean, I talked about at the equator, it's horizontal. So, but it's not the real equator, it's the magnetic equator, which is that green line. That's the places on the planet where that will be perfectly horizontal. And in different places, like around here, it should be something like 60 degrees or 70 degrees, and so on.
Frank, pardon me, this chart changes from time to time, doesn't it?
Yes, it does.
Yes.
That's why I said it was taken in 2011.
Yeah.
Ah.
And so then the thing that you're really interested in is what's the error from your compass to the true north. Now we're in pretty good shape over here in Perth. It's only a couple of degrees. If you can just use your compass, you don't have to correct it. Whereas down here we've got a bit more to worry about. We've got 12 degrees difference between where our compass points and where the north really is. But it's no big deal because it doesn't change that. When I say this was taken in 2011, it'd be not that hard to pick by naked eye the difference between that one and the current one. But nevertheless, you can always, you can get tables of what direction you have to, correct your compass needle for. Don't take it as gospel that north is where it points. You just say, oh, well, around here it's 12 degrees, we'll adjust our compass to allow for that.
So if you compare, this is not for me, but the gyro compass as opposed to the magnetic compass.
Gyro compass doesn't have this problem. Gyro compasses
That's
work.
what I'm getting at. So is the gyro compass relatively more accurate?
Absolutely, yes.
Yep.
Yeah. Well, the other thing about your magnetic compass is you do not want to have a bit of iron in your pocket. Don't put your key ring in your pocket near and then hold your compass there. I mean, there are lots of things that will upset. Or don't use a compass in a car. You know, it's okay in an aeroplane, they're mainly not still. But you know, I wouldn't advocate really as a compass for a way of figuring out where the hell you are, except if you've got no other choice. Like if you before GPS was invented, or before gyros were invented, or before all of that. If you had no other choice, then yeah, sure.
The ship's compass has got those balls, gimbals, I think they call
Yes.
The Kelvin's balls.
What do they achieve?
That's another.
All right.
Lock that in now. There's another inertial navigation.
Yeah.
Fantastic topic.
Yeah.
I love it. So, thanks Mel for reminding me of this fact. Actually, the Earth's magnetic field is wandering around. It's not stable, and we can see why that is in a while. So this is just the history of where the magnetic North Pole has been. It's wandered around a fair bit, as you can see, and it's still in motion. But it's not a big effect, because if we're looking for the North Pole from here, the fact that it's moved a little bit, it doesn't really affect your compass that much. But nevertheless, it's an important thing. And the strength is changing as well. I can't remember, there's somewhere in North America where they've been logging the field strength. Well, it must be in Europe, it can't be North. I can't remember where it was. I'm sorry. It must be in Europe where they've got enough history to keep track of the strength. So this has to be at one point on the Earth's surface, because it's different everywhere. If you put a magnetic field measuring device at one point and just look at it with time, that's what it looks like. Is that what I want to show you? So here's a nice contour map of what the direction's been doing. What's your compass error in different years? I'll just let it play. It's kind of fun to watch.
Can you predict the future, or can you predict where it'll be in 5 years' time?
I don't think so. Not very well.
You just have to say it's here.
You can. Well, with that previous thing, it's been pretty good. Those dotted lines were predicted from this. This solid line here is something else, but that's the prediction. So it hasn't been too bad. Because this was made in 2007, so prediction based on this line, it's not, so you can get some. Okay, I think this is probably time to take a break. Are we ready?
Yep.
Humans understanding how the universe works is one of the most artistic activities you can conceive. So the Earth's sphere interacts with radiation from the sun, called the solar wind. The sun doesn't only give out light, it gives out radioactive particles. And if you're somewhere out in space, you're bombarded by these, and it's quite dangerous. It's one of the biggest problems in the space station is to protect the astronauts from the radioactive particles from the sun. So we're pretty good on the Earth, so what's going on? What's helping us? So this picture is just about, I don't worry about the details, this picture shows that there's an interaction between the Earth's field. And it's actually quite a familiar phenomenon. Everyone knows about this. This is the aurora, this is the borealis. Beautiful photograph. And I couldn't help myself. I'm sorry, I'm going to bombard you with photographs about the Earth being bombarded by radioactive particles. So there's another photograph, absolutely gorgeous.
Wow.
And these are all taken in the northern hemisphere, as is that one, called northern lights, and they happen near the magnetic pole, as a clue, what that might be causing them. And there's the southern lights, again, happens near the south magnetic pole. And they're absolutely beautiful photos of a really important phenomenon. It's a magnificent spectacle, but it's also the thing that's keeping us alive, literally. So what's going on? Well, here's what happens at a fundamental level when you've got a charge, the little thing there, Q, standard. This is a charge, it's moving, and it reaches this coloured area there where there's a magnetic field. And the magnetic field, this is the tip of the arrow, field lines are pointing towards you, but don't worry, they're not dangerous. Magnetic field's pointing, so there's field lines all over the place, and if the charge is positive, you can use your right-hand rule, V cross P, and it goes around in clockwise circles, and if your charge is negative, it goes around in the opposite direction. So that's what happens when a moving charged particle enters into a magnetic field. So what? Well, here's a demonstration. There's an evacuated glass jar with a source of electrons and a big magnetic field, and there the electrons are going whizzing around in beautiful circles. If you were to impart some oblique velocity to these electrons, so they're not perfectly tangential, then of course you get a spiral, except they collide with the walls of the tube and they wouldn't last. But so if you direct them exactly at right angles to the field, they go around in a circle. If you make them a bit oblique, they'll do a helix. And that's really important. Here is what I was saying. It's really important that when these particles from outer space, from the sun, encounter the Earth's magnetic field, they start whizzing around in helical paths and eventually end up following the field lines, the magnetic field lines, end up at one of the poles, the north or the south pole. That's why the northern and southern lights occur. So what's happening is that it's two things. When you look at a scale drawing of the Earth, the atmosphere is crazy thin skin, and we're relying on the atmosphere to intersect these radioactive particles and keep us safe. And if they went straight through a mere effectively 10 kilometres of air, they'd hardly lose any of their energy and we'd all be dead. So what these magnetic field lines do is they increase how far the particles have to move in the air before they hit the ground. And so the further they move in the air, the more chance they've got of bumping into an air molecule, nitrogen typically. And when they bump into a nitrogen molecule, they lose energy, emit this beautiful light, and so it's wonderful. We get this artistic spectacle, plus we get to stay alive.
So we can see the artistic spectacle.
So we can appreciate the spectacle.
Just a little bit of trivia. That aurora, the people before the physics was known believed it was the souls of the party going to heaven.
Well, indeed it is. Okay, so the Earth's magnetic field sure is useful, but what makes it? Well, until the last couple of decades, there was only some speculation of what produces the magnetic field. Well, we know you produce magnetic fields by moving charges. You can have them in a wire or a loop. So somewhere inside the Earth, there must be moving charges, probably circulating, because it looks a bit like a bar magnet, which in turn looks a bit like a solenoid. So we're thinking that probably what's going on is there's circulating charges in the core of the Earth that are producing the magnetic field. Is that possible? Now this is the diagram. On this scale, you cannot even perceive the line that represents the Earth's atmosphere. I mean, this radius of the Earth is 6,000 kilometres. The half depth of the atmosphere, that is when it's reached half its density, it gets weaker and weaker as you get further away, is only 10 kilometres. So we look at the 10 kilometres out of 6,000. Anyway, so it's pretty well known from lots of geological measurements and other measurements on the behaviour of the Earth that it's got a rigid outer crust, a fairly rigid mantle, but it's not that rigid that you can't have continental drift and plate tectonics and separating ocean floors and all of that beautiful stuff. This is not a geology talk, so I won't say too much about that. And then it's mainly iron inside the Earth, and it's liquid. It's iron in molten form, except right in the middle, the pressure is so great from all the iron liquid surrounding it that even though it's a very high temperature, it would normally, if you had that iron on the surface, it would be molten, but it's pressed so much it remains a solid. It needs to be much hotter still to become liquid. Anyway, so the possibility is that in that liquid core, iron's a conductor, even in liquid form, it's a conductor of electricity. So charges could, in principle, move. And then, of course, it's complicated by the fact that the Earth itself is spinning. So there's going to always be an interaction between, if there are circulating currents in the molten core, they'll be interacting with the spin of the Earth itself and make complicated vortex patterns. So what we're looking at here is the dynamics of the molten morass of iron in the core of the Earth, circling like vortices in a very chaotic and very difficult to actually accurately model and predict what's going to happen. The other side of the equation that you need is what is it that's inside the molten core that's separating the charge, because there's no point just moving the entire atom. You won't produce a magnetic field that way. You've got to separately move the electrons and the nuclei. But because it's a conductor, you can do that. So there's some mechanism which is not too well understood. The turbulent motion of the molten core plus a little bit of charge separation can, in principle, generate a magnetic field. But of course, there's nothing in this physics of the molten core that says which direction is going to be the one that the most of the circulation occurs in. It may or may not be related to the spin axis of the Earth, and we'll say a little bit more. It seems to be mainly related, but the spin axis of the Earth, the iron's effectively neutral, so it could easily be one way or the other. So typically, the magnetic field of the Earth is aligned with the spin axis, but not exactly, not always, and it can be different. So, in the last few decades, you can't do this, you can't write down a single equation for what's going to happen when you've got this molten morass of iron circulating in turbulent patterns in the centre of the Earth. You cannot write that down as a simple equation. All you can do is write down millions of equations and solve them in a computer model. You make a computer model. And so about 10 years ago, these computer models started to come out. This is a graph showing pictorially the magnetic field computed by a model which takes into account the density of the molten iron, the viscosity of it, puts in an arbitrary fudge factor for how much charge separation is between the electrons, and that's a fudge factor. It's not known why that separation occurs, but you put in the right kind of fudge factors, and your supercomputer, after running many days, will churn out a picture like that, which doesn't look that different from the actual observed magnetic field. So I think they're on the right track, but it's a little bit like predicting weather. You can never get it exact. All you need is a bigger computer with lots and lots of equations, and if you put enough ingredients, you can make something that forecasts the weather at least for a few days. And if you put enough ingredients into this molten core, model, you'll generate something that looks like a real magnetic field. And it's very sensitive to the starting. You always start these computer models with some initial state. You know, you say, this is where the molten atoms are, this is where the charges are, let them rip. And then after a few days of computation, you get a picture like this. And then you do the same experiment again with different starting. The charge separation is slightly different. The initial motion of the atoms is slightly different. And you'll get a, where there's no, in this one here, it's a nice one because there's a dominant north pole and a dominant south pole. And there are a few other little jaggedy things. And this next one, it's got no dominant pole. There's just poles all over the place. It's not a single bar magnet, but lots and lots of bars. And then they did another measure, where now the north pole is at the bottom. So it's completely flipped. So that kind of tells you that, yeah.
It's not the core, the very central solid core.
No.
Isn't that
well, it's part of the core. The core is in two bits, the solid bit in the middle and the molten bit.
Surely this is not taking into account anything that happens because of the solid bit in the middle. And surely that's got a lot of iron in it. And
Yes.
It's got an effect.
It probably has. I think the models include, because it's not an abrupt change, I think the models include. I mean, the models include everything about the iron core.
Okay. You're just talking about the molten part.
Yes, well the molten part is the most important in terms of generating the currents. So, oh my God. Well, that turns me right for not bringing my HDMI adapter, doesn't it? Well, well, here we are. Here we have what's meant to be a timeline, but it's okay. We can get there. This is going to be. I'll put it up on my screen later on. This is a timeline from the present here, going back in time, and these bands are effectively the direction of the Earth's magnetic field, whether the North Pole is at the north or at the south. So when it's black, it's like it is now, with the magnetic South Pole near the geographic North Pole. And this time scale is about, I'm not sure where this cuts off, but the time's that probably several million years.
What are those words there, Frank, on the right? The ones that are sideways.
Yeah, can you see that scale? Anyway, it's probably 5 million years or something, the scale of that. So how do you know? Well, the thing is, geology works in your favour there because there's always sedimentation occurring. Rocks are being formed, sedimentary rocks are being formed all the time. And if the sedimentary rocks contain any magnetic materials, they will be preferentially aligned with the present state of the Earth's magnetic field. So once they get solidified, they're stuck. They become tiny little permanent magnets. The rocks are tiny little permanent magnets, which you can then dig up millions of years later and measure their the direction of it. Keep carefully labeling them as you dig them up, and then measuring their magnetic field, the direction of their magnetic field, and you can put together a time history. But nature has been extraordinarily kind to us, because the way that sedimentation works, it's just ongoing, building up layers and layers of sedimentary rock. And now we've got sea floor spreading on our side. You know, the continents are always moving, and they're moving. As they move, the sea floor spreads and becomes a continent later on. And as the sea floor spreads, it's peeling off the layers of the sedimentary rocks. And they're spread out on the sea floor in time, layer by layer, like a time sequence peeled open for you. And all you've got to do is get a ship with a magnetometer dangling from it and just scan across the ocean floor, and in a very short time you build up a picture like that, seeing the field reversals where it's trapped in the stratigraphic regions of the seafloor, which has been fanned out for us for our convenience, saves you digging a hole, all older layers, and trying to keep track of which direction that core sample came from. That's really hard work. On the floor, it's just there. The ocean floor, it's just there. It's just a beautiful thing. And there are some anomalies, of course. It's not a nice clean signal, but it's distilled into a picture like that. And I was hoping this up. The other picture was meant to look a little bit like this, horizontal timescale, and I just wanted to compare that. So that previous slide was 5 million years. On this scale, that's about there. Right, so that's why that slide is called, maybe you didn't even see, the recent history. It's only 5 million years. And to put it into context, this slide is about, when did life, so the first single cell life occurred 4,000 million years ago. So that really is a fairly recent map of the Earth's magnetic field. It's presumably been doing that further and further back. And the trouble is, to make those really old measurements of the magnetic field is a little bit hard. But there have been some measurements made, and hopefully, okay. So no, this is working. That's good. So this is a complete history of the Earth. Here we are now in this. And it's of course broken into different epochs and eras and periods, etc. It's all subdivided, and the subdivisions are sort of a bit arbitrary, but they're based on mainly what's going on, what kind of rocks have performed, what kind of life exists. And what we can do is we can zoom in, because we don't have magnetic history that far, but we can zoom in and look at just this part expanded. So that's only going back 500 million years, still longer than any accessible magnetic field record. So let's maybe zoom in on this one. Okay, now we're going. Okay, with this, I think magnetic field data inferred goes back about 180 million years. So there have been field reversals documented for the last 180 million years. So it expands this geological epoch of the Earth, or era of the Earth. And you can't see, but these are hundreds. There's also millions of years, yeah. Mm. And then finally, the really recent history, there are thousands of years, so that's quite recent. So the first slide of the magnetic history is kind of on this scale, except a bit distorted in my slide. Thank you, Mr. Gates. So, as I said, there's data going back to maybe 170 million years, and it's labelled by the eras in the. But of course, the paleomagnetism mafia have got their own naming convention for the different periods of time. So all these times are to do with the naming of the magnetic field. The other names are the standard geological names. And just so you can compare it nicely with the biological one, or the geological ones I had before, I just mirror image this so that new now is here, older is to the left. And I've replicated this picture with all together so that we can easily see, again, now is here, previously is to the left. And so I can flip between them now. So we're going back, say, look at what happened 60 million years ago, about there. 60 million years ago, so we're looking about there in the Paleocene era. So there, there have been magnetic field reversals documented during that entire record.
I recall Bruce saying, my cousin who's also a physicist, saying that we're due for another reversal. How the hell do they know? It's such a tangled mess.
You can't know.
It's a mathematical probability.
The chance, it's like when you're playing poker machines, you're due for a win,
Oh, I see.
What is instantaneously, or will it take a period of time for this reversal to occur?
Oh, how long does it take?
Yeah, but it got snapped.
No, it doesn't. It takes thousands of years to occur. And in fact, looking at, I don't have any detailed pictures, but looking at the models that are presented now, the evolution of the field from north that way and south that way to flipping can either be really sudden, like 100, I think about 1,000 years, where it just does a flip over 1,000 years, and it just flips pretty quickly, and its field strength remains pretty high. But there are other models which show the field collapsing, and then making lots, like that middle picture, lots of poles, and that's a really dangerous period to be in because you're not protected from the solar radiation during that. There's been some work, but hasn't really anything concrete turned up. Whether you can identify any mass extinctions with those periods of low magnetic field, and I think the problem is that the time scale for the field reversals is very grainy, and so you don't have enough detail to know.
But what I've heard is that when you're doing that flip, that the solar radiation causes havoc with your electronic equipment.
Oh, yeah. Cool.
And your satellites and everything else we've come to rely on. Is that
Well,
the
I mean,
outcome of it?
You don't need a magnetic field reversal to. I mean, the radiation from the sun isn't some nice uniform thing. There's things called solar flares. It comes in bursts, and that's why the aurora aren't just some uniform green light. It comes in bursts when there's a solar flare. The sun gives off more radioactive particles than normal in a solar flare. It's basically a nuclear explosion. And so then you get more particles hitting the Earth, and then you get a higher. And of course, the solar flares can create havoc in engineering systems, for sure. And they do.
Are the magnetic properties of the solids, are they permanent? Do they change? Once you've got, if you have a magnet, a piece of earth, neodymium or whatever, that's magnetized for the rest of time, isn't it?
Pretty much. Yeah. You've thought about the sedimentary magnetron. Yes, there's always, you're asking how permanent is a permanent magnet, really. And you know, probably those who went to school in the same era that I did, you know, if you made a magnet out of a piece of iron and you hit it with a hammer, the magnetism disappears. If you take a modern supermagnet and hit it with a hammer, it won't disappear. It depends on the chemistry and the structure of the and sedimentary rocks don't demagnetize. They're not very strongly magnetized to start with because they're pretty weakly magnetized. You need a sensitive magnetometer to see these magnetic signals on the Earth's floor. So I think the dissipation of the magnetic field is very, very slow and not very strong.
I heard the radio broadcast, Radio National. I noticed some strange effects in a kauri tree in New Zealand.
Sorry, I'm going to come close.
A strange effect in a kauri tree ring, kauri in New Zealand. And they looked into this, and they almost, according to this program, they pinpoint a reversal, in their opinion, at about 46,000 years, or just over. And I just wondered if you...
It's possible. I would like to show you my recent history map, but it's not... You can't... I don't think you can construct any... So is that... I don't think that's 40. but yes, it's quite possible that there was a field.
700,000.
Sorry?
Last reversal was about 700,000.
Right. Okay. So so there we're talking 300,000 for that line there. It's certainly possible that you can freeze in magnets in more than just geological system. You can freeze them into biological. I mean, let's face it, birds navigate with magnetic systems. Who knows what happens to bird navigation when the pole reverses?
Get lost.
They've got to survive the pole reversal to start with. Yes. Yeah, well, that's really the end of my formal presentation. And
Frank, is there any reason given for that huge period of stability?
Yes, lots of people have. It's like any random process. You'll always find someone that can see a pattern in a random process. But if you subject these data, skimpy as it is, to any rigorous statistical analysis, you can only conclude that it's random.
That it is a series of events.
You know, the probability of something systematic going on is very small, and that's why I think the ability to predict is negligible. You know, if you can predict for a short term, you know that if the field strength is 50 microtesla now, in 20 years' time it'll be between 40 and 60. You can sort of, because you know the speed at which it changes. But to predict it further than that, I think it's completely impossible.
Just two little things. One is that it's been found that sheep and cattle, when they sit down for rest, will very frequently align themselves to the magnetic forces of the Earth.
Wow.
As studied by satellite, they've just looked at a snapshot and they all line themselves up. Why, I don't know. It's a good thing apparently. You bed, you line it up certain ways, yada yada.
How do you know it's not aligned with the sunlight axis?
Or the prevailing wind.
I think they reckon the moves with the.
But I mean, it's
moves with the lines.
Yeah.
Anyway, it's just a general thing. The other thing is, what impresses me about this whole thing is something I've mentioned in a few of my talks, is that everything is related to everything else.
Indeed.
It is. And it's quite amazing how we actually put all that together. Yeah, thank you.
Yeah.
There have been some suggestions that reversals are related to perturbations from things like subduction and boloid impacts. What comments on that?
Yes, there's been a little bit of work done on that. There may be triggers what is correlated with a reversal, and there have been some ideas that there might be terrestrial geological events that trigger a reversal, and there have even been events in the solar system that could be correlated with a reversal, but there hasn't really been a mechanism proposed for how that might work. At this stage, people are just looking for possible correlations between the reversals and other things. I think we need more of them.
Frank, are there other planets in our solar system that have magnetic fields?
Yes, there are. Yeah, most of them, the ones that have a molten core, have all had magnetic fields. I can't remember which ones they are off the top of my head, but they're all. I think Mars doesn't any longer have a molten core, so it has no magnetic field anymore.
Jupiter is one that does, I think.
It's what is?
Jupiter is one that does.
Yep. Yes. Yeah, I think. Yeah.
Can I just read you this? There's an article in the New Scientist just recently. The magnetic field around the black hole, the magnetic field around the black hole is ordered, which means it can launch powerful jets of matter. So the correlation between the Earth and, say, a black hole in terms of its magnetic propensity, if that's the right word.
You need a black hole pretty nearby, though. You need a black hole nearby.
I don't understand this, but I'm just asking the question with regard to other field
Well,
within the universe?
I think if you could easily detect a black hole by its magnetism at the Earth, then black holes would have been discovered a lot sooner. So I think so that already tells you that at the Earth, the magnetic effect of any black hole that's known is tiny. I mean, yes, it's locally to the black hole. There's classifications of black holes where they are magnetized or not, whether they're spinning or not. So close to the black hole, they've got crazy magnetic fields, but I don't think you can detect them here.
If we could, we'd probably have more to worry about than our magnetic field.
That's right, yeah.
Frank, a few minutes left. You've mentioned your right-hand rule several times.
Yeah.
How long does that take you to give a potted version of?
Oh, okay. All right.
Can I get my question in first?
Yeah, go on.
I was going to say, is it critical to have iron in this or molten?
It doesn't have to be iron, no, but it probably needs to have ferromagnetic properties.
But it's the molten and therefore the swirl.
Yeah, the turbulent fluid dynamics is what's required.
Well, that's the reason my question about a black hole, because we're dealing with something totally different, aren't we?
Sorry.
We're dealing with something different in a
Like
black
I say,
hole.
that was the reason for my question. We're talking about, molten iron and all the rest of it.
Yeah.
But the black hole theory, it doesn't replicate that circumstance, does it?
No, but there are charged particles. So when a black hole collapses, there are charged particles. And whether it has spin or not determines whether it's magnetized. Just before it collapses.
Right, thank you.
Okay. Just like the magnetic field is a figment of the imagination, it's a human construct to try and help us explain, the field itself has all the pictures that I drew show arrows on the, you need to be able to attribute a direction to the magnetic field. If you get the strength, you need a direction as well. So when you have a current flowing in a wire, like this one, and you've seen the diagrams of magnetic field lines circulating around, the question is, because they're going completely at right angles, how do you figure out what the direction of the arrow is? Is it clockwise or anti-clockwise? Because going from that direction to a circulation, and doing that, is it that way or that way? And it's totally arbitrary. How can it be arbitrary? Surely your experiments. No, it's totally arbitrary. Remember, the field is a construct. And when you say this current going in that direction makes a field going in that direction, you use your right-hand rule. You say you line your thumb with the current and your fingers point in the direction. That's the right-hand rule. If you use your left-hand rule, they'd be going the other way. Right? It's arbitrary. So we'll choose the right hand, because most humans apparently are right-handed. Choose the right-hand rule to define the direction of the field. How can that be? The field has measurable effects. How can you arbitrarily assign a right or a left hand to it? Well, the answer is simple. The field isn't a real thing. It's an figment of imagination. To get from the field to a force, you have to use the right-hand rule again, because the force depends on the velocity of the charge, and so you've got the field and the velocity. You use your right-hand rule to get the force. And so the force is always the same whether you use a left-hand rule both times or a right-hand rule both times. So anything you can observe, you have to use the rule twice. And if you use your right hand once and your left hand the second time, you get the wrong answer. As long as you always use the right hand rule or the left hand rule, you'll always get the observed effect. Plotted enough?
Yeah, I just want to make one comment. Since the Apollo lunar days, astronauts have noted that if they close their eyes, they see flashes of light inside, the Cherenkov radiation. So one creative astronaut on the space station decided to experiment with this. So what he did, he lay down between, they've got lead storage batteries on the station, so he put his head between the lead plates there, and he was counting the number of flashes he get in his eye, and he noted no difference. Whatever orientation he placed, he still saw the same amount of flashing in his eyes.
Right. Wow.
With electric motors, wanting to go to the opposite direction, is that what you're doing with the field of electricity?
Yeah, there's your right-hand rule in the motor to get the direction of the field produced by the current, and then that acts on a permanent magnet. You use the right-hand rule again, and you'll get the correct direction of the electric motor. You've got to use it twice.
But then to go back the other way,
As a generator, you mean?
on an electric motor,
You reverse any one thing, you reverse the final. So if you reverse the current, the motor goes the other way.
reversing the current, right.
Or if you turn the magnet around the other way, the motor will go the other way as well. Depending on what, I mean, motors are complicated, but these are permanent magnet motors.
Well, ones I've been used to is you just turn the switch,
Yeah.
and you go from right-hand drive to left-hand drive.
Yes, of course. You're just reversing the current.
Right.
Yep. If it's a DC one. Anyway.
Okay,
I think
that looks like it's about it. We'll tune in for our very last scintillating U3A session with Merv this afternoon at 2 o'clock.